Welcome! In this video, we will explore Ion Optics acquisition add-on modules for IonWizard, ideal for recording cell contractility in primary and cultured cells. We will start with a list of recommended modules for various sample types, followed by detailed explanations of each module, including algorithms, best practices, and brief demos. Finally, we will compare these modules head-to-head using primary adult cardiomyocytes and induced pluripotent stem cell-derived cardiomyocytes, iPSCs for short. Ion Optics offers 3 acquisition modules for evaluating contractility in isolated and cultured cells. That includes Sarcomere Length, SoftEdge, also known as Edge or Cell Length, and CytoMotion. Each module comes with distinct advantages and limitations, tailored to specific cell types and experimental conditions. Our modules empower researchers to assess contractility in diverse cell types, including primary adult cardiomyocytes, primary neonatal cardiomyocytes, cardiac slices, iPSC cardiomyocytes, and 3D cultures like organoids and spheroids. In this video, we will mainly focus on primary adult cardiomyocytes and iPSC's cardiomyocytes. However, we acknowledge the versatility of each contractility module applicable to various sample types. If you have any questions regarding other samples, please don't hesitate to reach out to us at info@ionoptics.com. Our discussion will start with the Sarcomere Length module. The Sarcomere Length module is the optimal choice for detecting contractility in isolated, healthy adult primary cardiomyocytes, because sarcomere length is a more consistent, absolute measurement when compared to cell length. It also proves invaluable in measuring diastolic sarcomere length in cardiac slices ranging from 100 to 200 micrometers in thickness. To gain a deeper understanding of the algorithm utilized, let's briefly revisit the structure of a sarcomere. A sarcomere is defined as the space between adjacent Z-lines within a muscle. Z-lines can be challenging to optically resolve. However, the A band containing myosin and the I bands containing actin are readily distinguishable and can serve as markers for sarcomere spacing. The Sarc Length module employs a fast Fourier transform to compute the mean frequency of sarcomere spacing, as defined by the A and I bands. Consequently, the values obtained within a user-defined region of interest represent the mean sarcomere length across all sarcomeres within that region, and these measurements are reported in micrometers. For more comprehensive information about the algorithm, please refer to our linked application note. When you are using the Sarcomere Length module in IonWizard, you might be wondering about the significance of the lines you see on the screen. We will provide a brief explanation here, but for more in-depth details, please refer to our linked application note. First, there is the ROI, which stands for Region of Interest. You can select this area by adjusting the size of the magenta rectangle and its position. Within each ROI, we collect signal intensity, or raw data, displayed as the black line. This data undergoes mathematical processing to create windowed data, represented by the blue line. Please note, if you increase the microscope's light intensity, both lines will move upward. To ensure the best results, keep them both visible within the graph area and above the midline. The window data, in combination with calibration constants, generates the power spectrum, depicted as the red peak. Ideally, you should aim for a single red peak positioned between the 2 green lines. Achieving this requires proper alignment of the cell, ROI, and the green lines. The green lines serve as scanning boundaries for the region of interest. For the left-hand green line, avoid positioning it too far to the left, as this can reduce intensity and increase noise in your red line and peak. Also, avoid having it too close to the red peak, especially if you plan to measure sarcomere length before and after adding an agonist such as isoproterenol. The exact placement of the right-hand green line is seldom crucial, as long as it is sufficiently positioned to the right. When the cell and alignment are in good condition, there is typically minimal high-frequency noise. If you'd like to delve into the detailed calculations behind these lines, please check our linked application note. For optimal sarcomere length acquisition, it's important to follow these best practices. 1. Avoid having multiple cells within the field of view to ensure accurate measurements. 2. Select the appropriate ROI size. When selecting your region of interest, avoid making the magenta rectangle too small. Aim for an ROI with more than 6 sarcomeres. Increasing ROI width will provide the algorithm with more sarcomere data to work with, so it is preferable to increase the width of the ROI. Increasing the height of the ROI could introduce additional noise because alignment of sarcomeres may not be identical in different regions of the cell, so it is recommended to have narrower ROIs. 3. Have a proper cell positioning. Position the cell in a way that its sarcomeres are parallel to the longitudinal axis of the ROI. Ensure the cell is well focused to achieve a single red peak as demonstrated earlier. And 4. Green line placement should be as we discussed previously. Ensure that your green lines are correctly positioned to define the scanning boundaries for the ROI. By following these guidelines, you can enhance the accuracy and reliability of your sarcomere length measurements. Let's walk through a practice run using the standard calcium and contractility system to demonstrate the correct data collection process with the sarcomere length module. Begin by ensuring your aperture is closed to have just one cell within the field of view. You can adjust the aperture or field of view size using the knobs on your cell framing adapter. Position your cell correctly. If needed, you can physically rotate the camera in the standard calcium and contractility system to align your cells properly. Now you need to select the region of interest. Grab the magenta rectangle that defines your region of interest and place it over the cell where sarcomeres are visible and well focused. Make it slightly wider to contain a greater number of sarcomeres. Now, let's position our green lines. Sometimes, the right-hand side green line is pushed to the right edge. We can move it slightly towards the center. The left-hand side green line might be too far to the left as well, affecting the intensity of the red peak. Move it slightly closer to the red peak, ensuring it's not too close to it. If you wish to adjust your region of interest, you can move the magenta box around to explore different areas displaying similar peaks, and then select one that you're satisfied with. Once you're content with the positioning, you can initiate the experiment, and you will observe a clear sarcomere length trace. Following these steps will help ensure accurate and reliable data collection. While sarcomere length module excels in detecting contractility in primary adult cardiomyocytes with clear sarcomeres, it's important to recommend the SoftEdge module as well. The reason is that in certain cases, such as when working with diseased models, isolated primary adult cardiomyocytes may not exhibit distinct sarcomeres. In such challenging scenarios, the SoftEdge module becomes invaluable. SoftEdge is not only beneficial for diseased models, but also finds utility with other cell types that lack clear sarcomeres or do not display clear sarcomere patterns. Next, we will closely examine the SoftEdge module and its two available options. The SoftEdge module, often referred to as Edge, is a tool designed to precisely identify the left and right boundaries of objects, such as cells, within predefined detection limits relative to the left side of the image. It then quantifies the displacement of the object in micrometers. Edge module can be applied to various cell types. In this section, we will illustrate its functionality using primary adult cardiomyocytes as an example. Edge offers two distinct options: the outside-in option, as represented in this image, and the box option. We will provide a detailed explanation of each, including practical demonstration videos, and conclude this section with a summary comparing the two Edge options. In the upcoming slides, we will discuss the concepts of the video area and the graph area. To clarify from the outset, the video area pertains to the region where your cell is visible, while the graph area lies beneath it. Starting with the outside-in option, outside-in stands for scanning from outer limit to inner limit to find a signal that fulfills specific criteria we set from Edge options. To clarify this, we need to explain the lines in video and graph area in addition to Edge options first. Within the zoomed-in red circle, you'll notice two lines referred to as detection limits. These are the limits of scanning. In other words, no signal outside these two lines will be scanned. Outer detection limits should be positioned in a way to have a stable baseline. So, don't have it too close to the cell edge, but also don't have it too far away from it. For the inner detection limits, you have more flexibility to position them further inside the cell. You'll observe another line known as the selected video line, which should be positioned at a location that gives you the highest contrast or the strongest peak in the graph area. So, for best results, while moving the selected video line in the video area, pay attention how peak changes in graph area between your detection limits. When you see a strong peak that doesn't go away as cell moves, then you are in a good position to detect the edge. Now, in order for the algorithm to scan for and detect the edge, we must choose an option for it, and we have several possibilities. The first option is below, which means that edge is detected when the algorithm finds the first signal below the horizontal line in graph area. The other option is above, where edge is detected when the algorithm finds the first line above the horizontal line. Option 3 is peak below, which signifies that a signal should start above the horizontal line, cross below it, and then rise again. Option 4 is peak above, where the signal starts below the horizontal line, crosses above it, and then goes down again. And finally, we have the lock option, which allows you to freeze one edge. This option is only useful if one side has poor contrast and cannot be tracked. Remember, if you lock an edge, the absolute change in length should be disregarded. Now that we explained all the lines and options, outside-in means that within the detection limits, scanning starts from the outer detection limit to the inner detection limit until your algorithm finds the first signal that fulfills the specifics of the edge options you have selected. From the point where edge has been detected to the inner detection limit, everything is ignored. That's why your inner detection limit location is more flexible than your outer limit. It's worth noting that achieving good peaks in graph area depends on having cells with well-defined boundaries. This module can be challenging when working with iPSC's cardiomyocytes or cultured cells lacking clear boundaries, as we will demonstrate later in this presentation. Before we practice using the outside-in edge module with primary adult cardiomyocytes, let's have a zoomed-in look on the best locations for your horizontal line for each edge option. We will use the left edge as it has stable peak above and peak below. First, this is your baseline where the hand is. You want to make sure that your baseline from the outer horizontal limit isn't crossing the horizontal line, as that will affect edge detection and cause noise. We will just show now where each horizontal line will be best suited for the option selected. As you see, if we pick above or below, we can be closer to baseline, and if we choose peak above or peak below, we have to be a little bit further from the baseline and closer to the peak itself. In our practice run, we have one cell within our field of view, and it's positioned in a way that the cell's edges align with the detection limit lines. Let's proceed by dragging our left edge detection limit lines, or the red lines, and position them along the left edge of the cell. First, we need to find the area on cell edge with highest contrast, or the largest peak in the graph area. So I will just be moving the video detection line across the left edge until I find that area with the strongest peak. Next, we need to monitor the graph area and make sure that the contrast is consistent throughout the contraction. We don't want to lose our largest peak as the cell moves. This looks like a good location. Now we need to pick a threshold option in the graph area. We can use below or peak below on this side. Now we will set the right edge in a similar manner. Here it makes sense to use above or peak above options. Once everything is set, let's start the experiment. To maximize data visibility, you can press Alt and quickly press letter A twice. This sets the automatic limits to scale the y-axis of your traces. Now let's take a look at the traces. The top trace represents the left edge, the middle trace indicates the right edge, and the bottom trace corresponds to the cell length. You might be curious why left edge increases while right edge decreases during the contraction. To explain this, it's crucial to understand that the movement of cell edges is relative to the left side of the image, where the reference point is. So, when a cell contracts, its left edge moves inward, which increases the distance from the reference point. Consequently, the left edge trace rises as the cell contracts and then returns to its original position as the cell relaxes. The right edge behaves in the opposite manner. When cells contract, the right edge moves closer to the reference point, reducing the distance. Consequently, the right edge trace declines during the contraction and rises again as the cell relaxes. Cell length represents the difference between the distances of the two edges from the reference point at any given time. Therefore, cell length also decreases as the cell contracts and increases as it relaxes. The SoftEdge box algorithm functions similarly, yielding comparable outcomes for right and left edges, as well as cell length when compared to the outside-in option. However, there are a few differences in the way edge detection works using the box option. In the video area, the size of the box remains fixed and is always centered between the detection limits. This means that you have limited flexibility in how much you can move the detection limits within the cell. This constraint can make using the box edge option challenging, especially with cells that exhibit strong contractions, as there is a risk of losing the edge out of the box when cell reaches peak contraction. The graph area is much simpler in the box option. Here, edge detection depends on scanning signal between detection limits and comparing it to the snapshot within the box for each edge. We recommend edge box option for cells that have subtle contractions, cells that do not have strong borders, or clusters surrounded by other cells because it performs line averaging and auto-scales all data. This removes out any inconsistency in contraction, which is a very common scenario with these preparations. When using edge box option, aim to have a single, clear, and large peak in graph area that moves. To enhance your peak, you'll need to adjust the box position in the video area. Let's proceed with another practice demonstration. Using the box edge option can be quite straightforward and smooth. First, ensure the cell is correctly oriented, as we've already done here. Second, place the red box or the left edge box on the left edge of the cell. You'll have a zoomed-in image on the side, which is the snapshot used to detect your edge. Observe the strong peak in the graph area. Now move to the right edge and position the green box on that edge as well, making sure you have a strong peak that is moving in the graph area. Now you can start the experiment. In our recommendations for selecting between the two edge detection methods, we have outlined specific guidelines based on the samples under consideration. If the sample is a primary adult cardiomyocyte with weak beating or short unidirectional movement, both the outside-in and box edge detection options are suitable choices. If the primary adult cardiomyocyte has strong beating or longer unidirectional movement, the outside-in option is preferable, as it allows for adjustments in detection limits to consistently contain cell edges. If you're working with primary neonatal cardiomyocytes, which often lack clear unidirectional beating and well-defined borders, we do not recommend the outside-in option, and using box option would be more straightforward. When working with iPSC cardiomyocyte clusters with well-defined borders, the box option is preferable due to line averaging and auto-scaling to remove any inconsistency in edge detection. If you are working with iPSC cardiomyocyte monolayers, neither the outside-in nor the box option is recommended. Instead, we suggest using CytoMotion module, which will be discussed further in the next section. Finally, if you're working with 3D cultures like organoids and spheroids, which typically exhibit clear borders, both edge detection options can be useful. However, we recommend using the box option in these cases as well for optimal results due to line averaging and auto-scaling to remove any inconsistency in edge detection. Despite the possibility of using edge detection with amorphous cell types, it may not always be the most suitable choice due to the considerable challenges associated with its application in many instances. So, we have developed an alternative algorithm called CytoMotion, specifically designed for use with amorphous cell types. This module offers a more practical and effective solution for analyzing cultured cell samples. In recent years, iPSC cardiomyocytes have become valuable tools for cardiac disease modeling due to their human genetic background. However, these cells, while advantageous, often present challenges such as immaturity, irregular morphology, and poor contrast in imaging. To address this, we've developed CytoMotion software. The CytoMotion algorithm monitors changes in pixel intensity within a user-defined region of interest relative to a reference frame in IonWizard. The selection of the reference frame can be carried out manually in IonWizard using the capture function for standard calcium and contractility systems, or automatically defined using MultiCell window for our higher throughput systems. Reference frame is identified as the frame with the least difference in pixel intensity compared to neighboring frames. This frame is assumed to represent the diastole phase of the cell's contraction cycle. To detect contractility, CytoMotion employs two methods: pixel intensity and pixel correlation. Let's discuss pixel intensity first. For every pixel, at each time point, the software calculates the difference in image intensity between that pixel and its corresponding pixel in the reference frame. Also, at each time point, the sum of these differences is divided by the number of pixels, resulting in the average pixel intensity for that time point. In regards to pixel correlation, for each pixel at each time point, CytoMotion calculates the correlation between that pixel and its corresponding pixel in the reference frame. The correlation values range from 1, where there is no differences in the pixels, to 0, where the pixels are completely different. At each time point, the software computes the sum of all these correlations and divides it by the number of pixels. So the result is reported as the average pixel correlation at each time point, presented as a correlation coefficient. Here are the mathematical representations used to detect pixel intensity and pixel correlation. Based on these equations, you will expect to have increase in pixel intensity trace when cells start to contract, while pixel correlation trace will decrease with contraction. Let's walk through a practice session with CytoMotion. In this video, we will select two contraction centers, avoiding clusters with well-defined borders, as these will be used for a comparative analysis between the Edge and CytoMotion modules later on. First, we need to define the region of interest. Then, we will manually capture the reference frame, as this is the standard calcium and contractility system. Remember, for best results, make sure that the ROI box captures only one center of contraction and that the ROI position should not overlap multiple centers of contraction. If cells are beating slowly, capturing the reference frame is straightforward. You should hit the capture button when the cells are in a relaxed state. A good indicator that you've selected the correct reference frame is that pixel intensity will increase with contraction, while pixel correlation will decrease as illustrated here. Now let's move to another area within the field of view. Remember, each time you want to take a measurement, you need to capture a new reference frame. You can verify if you've chosen the correct reference frame after capturing it by switching the view from video to plot. If you observe an increase in pixel intensity and a decrease in pixel correlation with contraction, you've chosen the right reference frame, and you can proceed with contractility detection. As you can see here, different contraction centers may exhibit distinct contraction profiles. Since edge detection is applicable to comparable sample types as CytoMotion, let's provide an overview of the advantages and disadvantages of each algorithm. The advantages of CytoMotion include that it is ideal for monolayer iPSC cardiomyocytes and cultured cells, including 3D cultures. It also captures contractility measurements that cover the entire region of interest, including centers of contraction. However, CytoMotion also has its disadvantages, and these include that the contractility data is reported in arbitrary units, limiting absolute value reporting to kinetic data. The other challenge with CytoMotion is selecting reference frames, which should be captured when cells are resting. This is challenging to capture when cells are beating fast. On the other hand, edge detection advantages include that contractility data is reported in micrometers, which is an absolute value, and edge also can be used effectively with primary adult cardiomyocytes. While some of its disadvantages are that it's not recommended for use with iPSC cardiomyocytes or any cultured cells lacking clear boundaries. It also can be challenging to use with clusters where boundaries have minimal motion, and the algorithm primarily detects unidirectional motion edges and cannot capture the center of contraction. Now that you have developed a more profound understanding of each module and its efficient utilization, we are ready to engage in a direct comparison between these modules when applied to primary adult cardiomyocytes and iPSC cardiomyocytes. Beginning with primary adult cardiomyocytes, we will evaluate the measurement of sarcomere length and assess both options within the SoftEdge module, applying what we learned previously. Now, we will perform a direct comparison between the SoftEdge and CytoMotion modules in iPSC cardiomyocytes using a well-defined cluster. You will notice that even with a well-defined cluster, using the outside-in edge is challenging to get a clear trace. Let's summarize everything and have one last look at best contractility modules to be used based on your sample. If you have adult primary cardiomyocytes that are healthy and show clear sarcomeres, go for Sarcomere Length algorithm as it provides absolute values with reliability, data reproducibility, and ease of use. If you work with diseased or genetically modified models where the adult cardiomyocytes do not show clear sarcomeres, then use SoftEdge as it is more reliable in these cases. If you opt to use SoftEdge, then your options are outside in and box. If cells are contracting in a way that the edge can be contained within the box area at all times, then use box module as it is more consistent and easy to use. However, if cells contract in a way that the edge cannot be contained in the box at all times, such as after adding an agonist that will increase inotropy, then use outside in, which is more flexible and can accommodate scanning a wider range of distance to detect the edges. If you work with amorphous cultured cells that have boundaries with low contrast, such as an iPSC cardiomyocyte monolayer or neonatal cardiomyocytes, we recommend using CytoMotion, as this module is better for contraction kinetics detection, ease of use, and it captures centers of contraction. Another option is EdgeBox, however, this is more challenging to use and will not capture your centers of contraction. If you work with 3D cultures, such as organoids and spheroids, we still recommend CytoMotion to capture centers of contraction and have more kinetic data, but using EdgeBox here is also valuable due to ease of edge detection and measuring its displacement in absolute values. If you have any further questions, please reach out to us at info@ionoptics.com.